Today we want to talk about line integrals. More specifically, the parts that we need to understand a line integral, so that we can figure out what line integrals can be used to calculate. Let's start by reminding ourselves of how integration works. We integrate an expression over a set. This shows up in many forms. It could be the integral from a to b of f of x dx, in which case f of x dx is the expression, and the interval from a to b is the set. The idea is that we evaluate the expression at all the points in the set, then add up the results. This is a little bit fishy because our expression is usually changing continuously, and we're trying to plug an uncountable infinity of points into it. So when we talk about adding up the results, we normally think of addition as a plus b plus c plus d, where we can see the things that we're adding and separate them into a list, and then put a plus sign in between all of them. We can't do that, say, with an interval, because we're plugging in all the real numbers between a and b. And I can't make a list of all the real numbers between a and b. That's the difference between two types of infinity: countable infinity and uncountable infinity. So it's really weird that I phrase it this way: evaluate the expression at all the points in the set, then add the results. Another way to think about this is that we don't say that we plug infinity into an expression. That doesn't make any sense. Although we have a way to plug infinity into an expression, we just don't say it that way. We take the limit as x goes to infinity of f of x, and then sometimes we shorthand that by saying, let's plug infinity into this function, even though that doesn't make any sense at all. Infinity is not a number. We can't just plug it into a function. So if we say, let's plug in infinity, you'll think, what do you mean by that? Let's take the limit as x goes to infinity of f of x. And that's how we interpret the phrase plug in infinity. Equally weird to say, add up all the points or all the values of this expression at all these points, this uncountable infinity of points. How do we add something up if we can't separate it into terms? This is what we mean. We are integrating. Integration is this continuous addition. Integration is multiplication, but one of the factors is continuously variable. Integration is continuous addition. This is how we want to think about integration. Integration is just continuous addition. It's addition when I can't separate the terms with a plus sign, because there is no next term, because we're dealing with the real numbers. Any questions on the big picture? Here's the annoying part. Because I think this is an important idea and it takes time to assimilate into our way of thinking, I get to say this at the start of every day for the next week. We talk about evaluating an integral by evaluating the expression at all the points in the set and then adding the results, and taking this to mean continuous addition. Now all we have to do is come up with different expressions and different sets. We spent some time with some scalar functions doing double integrals and triple integrals, where the big challenge was describing the set so that the integral would understand. But we solved that problem by just saying, we just have to say what the variables are between. X is between a and b, y is between c and d, z is between e and f. So now we're looking for other sets and other expressions to perform integration on. That's the context with which we walk into this line integrals business. Here's a line integral. The line integral of a vector field f along an oriented curve C is the integral over C of f dot dr. So there's a lot to unpack here. Note that it fits the same description as all of our other integrals. We're going to evaluate this expression f dot dr, whatever that means, at all the points in this set C, which is an oriented curve. So curve just means one-dimensional thing. Oriented means it has a direction. There's a starting point and an ending point. A lot of times we name the endpoints P and Q. So C is the curve, P is the starting point. And Q is the end point. We introduced the concept of a vector field. A vector field is just a function that assigns to every point in the space a vector, not just a value, but a vector, a direction. The expression that we're going to integrate is the vector field dot dr. So the curve shows up in two places in our integral. It's the set of points. When C shows up over here in the integral part, it's just the set of points that we're plugging into the vector field dot dr. dr is also related to the oriented curve C. Emphasis on the oriented part because dr is going to be a vector tangent to the curve at a given point. And so what we're doing, all along this curve C, we're evaluating the vector field dot dr, where dr is a tangent to the curve, and adding up all those dot products. We're going to need to build a context in which we can have where we have a vector field and a curve running through a vector field. But first, we want to see that this description fits our generic description of an integral. We're going to evaluate the expression f dot dr at all the points in the set C. Set is an oriented curve. Any questions? Here are the things that we're going to need to make this make sense. Here's our to-do list. First of all, we need some examples of vector fields. It's easy just to say at every point we have a vector. What are some examples of vector fields? That'll help us build some context. With scalar functions, we can always just use length, area, volume, those kinds of things. So we're going to need some examples of vector fields. We're going to need to learn how to parameterize curves. We need a way to describe curves, sets of points in 2 and 3 dimensions. So we need to learn how to parameterize curves. This part of the program is related to describing the region or the solid for a double or a triple integral. I need to describe this curve in a way that the integral can understand it. And to that end, we're going to parameterize curves. By extension, we're going to need to be able to calculate tangents to parameterized curves. So we're going to have to parameterize a curve, and we're also going to have to come up with tangent vectors. Then the third thing we'll need to further our context is what's the dot product for? What are some examples of dot products that we can pair with our examples of vector fields so that our line integral has some kind of meaning? Less necessary for the calculation, more important for attaching meaning. As far as actually just calculating line integrals, all we have to be able to do is parameterize curves and calculate dot products. But that's just doing math in a vacuum. What do these things mean? That's going to be our big question. Any questions before we go on to our first thing, which is actually not going to be the first thing? How's everybody okay? Everybody looks stunned and very serious. It's because it's vector calculus. Oh, it's so different. It's all the same. It's just more integration. I always wonder if my calculus classes are heavily integration focused because calculus is heavily integration focused, or because I spent a majority of my teaching career teaching Calc 2, which is the integral calculus part. It's hard to say. Did one influence the other? Or would I always lean into the integral part? All right. Let's talk about parameterizing curves. For the purposes of line integrals, we need to parameterize curves so that we can describe these curves to an integral in a way that the integral will understand. So our motivation here is we need to describe curves to integrals. So our goal here is to describe curves to integrals. Here's what we want to do. A curve is just going to be a set of points in R2 or R3. I guess it could be a set of points in R whatever we want. But the important thing here is we're describing a one-dimensional set of Rn. So a curve is a one-dimensional set. The important feature here is not the space that it's sitting in, but the fact that it's one-dimensional. It's a one-dimensional set in our space. We're mainly going to be using R2 and R3. So that space is going to mostly be R2 and R3. The way we normally get into describing curves is we look at graphs of functions, and this is very limited. So our current technology is to think about graphs of functions. So we first start thinking of curves as graphs of functions. This is fairly limiting, and it produces certain geometric things that we don't really want. So if we write y equals x squared, where y is a function of x, that's going to be a parabola in R2, and that is certainly a curve. But this is a heavy restriction where one variable is a function of the other variable. This is restrictive. It's very restrictive to require that one variable be a function of the other variables. In addition, if I have a function of two variables, we're not dealing with a curve at all, we're dealing with a surface. So in addition, if one variable is a function of the others, then we have a function of two variables. If we have a function of two variables, we're no longer looking at a curve, we're looking at a two-dimensional surface. If we look at the graph of a function of two variables, we look at a surface, not a curve. So this function business is not going to help us if we're describing curves in R3. It might work out if we're describing curves in R2. Graphs of functions are curves in R2, but if we're in R3, graphs of functions are now surfaces. A surface is two-dimensional and a curve is one-dimensional. Moreover, when we have functions, this is a restriction because each input can produce only one output. For every x, there is only one value of y. So we upgrade. We stop just thinking about functions and start thinking about graphs of equations. This is a little bit more general because one variable need not be a function of the other variable. So the equation x squared plus y squared equals 1 is a curve in R2. It's a circle of radius 1 centered at 0, 0, and it is a curve in R2. It's a curve in R2 that is not a function. Y is two functions of x, or x is two functions of y. But it fails the vertical line test. Each input has two outputs, or up to two outputs. So we've generalized a little bit because now we don't require that that one variable be a function of the other. And in R2, everything is just fine. But if I have a function of three variables, or sorry, an equation involving three variables, I could be describing a surface in R3. So we have a similar problem to our similar problem that we had in functions. Our equation of x, y, and z is describing a surface, which is two-dimensional, not a curve, which should be one-dimensional. So we need to go one step further in describing curves in R2 and R3. And that means we're going to parameterize curves. Each coordinate will be a function of some parameter rather than related to the other coordinates. I can define the coordinates independently of each other. A parameterized curve A parameterized curve is going to define the coordinates independently of each other and instead write them as functions of some parameter. So we're not describing all the points with a relationship between x and y. We're just defining x as a function of some parameter, usually t, and y as a function of t, and then figuring out the point, plotting the points that way. So each point on the curve has an x function and a y function. Or if it's a curve in three-dimensional space, an x of t, a y of t, and a z of t. So I'm just making a bunch, telling you how to find points x of t and y of t. You plug t into each of the coordinates, and that's your point. And you plug another t into the next into your coordinates, that's another point. The important thing to note here is that we're plugging values of a parameter into 3 separate functions. And so that'll give us 1 point. And then when t changes, that'll give us another point. And if we keep doing this, we're going to build a one-dimensional curve in R3, not a surface. If z is a function of x and y, that's going to make a surface. If I have an equation involving x, y, and z, that's going to make a surface. But by doing things this way, I get a one-dimensional curve in R2 and a one-dimensional curve in R3, and that's what we want to describe. Two examples. First, our iconic example. Second, we have to demonstrate that this is backwards compatible with what we have with functions. This parameterized curve business should be compatible with the stuff that we have for equations and the stuff that we have for functions. How's everybody okay? It's the naming of parts. So math classes when it's the naming of parts are always worse than other math classes. I don't know if there's a hierarchy. Is there a tier list out there for math class types? Or are all math classes? I don't know, whatever the lowest tier is. I just realized that we use different tiers. Although with all the tier rankings that are going on, are we going to see a new grade appear? So instead of just A, B, C, D, and F, is there going to be an S grade that sits on top of them all? Because we're going to be like, well, A plus, that's just not good enough. They got an S. And then we'll combine that with the way that car manufacturers name things. Because they have sport mode, and then sport plus mode, and then boring mode. So we get sponsorship from BMW. It's like sport. They got a sport, an S grade. Then they got an S sharp. Or is that Mercedes? Someone does S sharp instead of sport plus. What I wonder is why at this school we have 2 failing grades. Why do we have D and F? There's no functional difference between a D and an F. It changes what your GPA is, but if you didn't pass the class, who fucking cares? You got to do it again. You know what I mean? Why do we have 2 of those? Is it? I mean, it seems like kind of a jerk move on our part. It's like, well, you didn't just not pass this class. You didn't just get a D and not pass this class. You have to do it over again. You got an F. You like really didn't pass this class. Why do we have that? Anyway. I also wonder why we have 3 passing grades. Why do we need that? That seems excessive to me. And then some teachers are like, oh, we got to have pluses and minuses. Why do we need 8 passing grades? If 8 passing grades is better, why don't we have 10 passing grades? If 10 passing grades is better than 8, why don't we have 12 passing grades? Why don't we have a continuum of passing grades? You know what I mean? Here's my argument that 8 passing grades is way too freaking much. Let's suppose that we're all wine experts and I bring in 3 wines. 1 super high quality, rare vintage. One that's just kind of a boring everyday wine that's cheap. And one that's like on its way to becoming vinegar and is disgusting. The chances are that a room full of experts would be able to say, this one is vinegar. Why did you make me drink that? This one is the middle of the road. And this one here is clearly the superior wine. And we would probably all agree. Now, if instead of just lining up those 3 wines, in between each of those 3 wines, I put 3 more, would we all come up with the same ranking? 1 through 9. I don't think we would. There are too many rankings for the rankings to have any meaning. That makes sense? There's no, like, if 3 is not enough, then 8 is not enough either. And none of it makes any sense. Now, it would be fine if we wanted to switch to just using percentages and use a representation of a continuum of grades, even though if we just use percentages out to the nearest units, that would just be 100 grades instead of 3 or 8. Or if we rounded to the nearest 10th, that would just mean there are 1,000 grades. And if we go to the nearest 100th, so you can get like an 88.75, there are just now 10,000 different grades you can have. Are we really making things more clear or less clear? And then if you got 88.75 in this class, would you still get an 88.75 in some other Calc 3 class? If the answer is no, then there are too many grades. Any questions? Now, ultimately, I don't really have a preference for whether we should have plus-minus grading or not. But when the idea of plus-minus grading came up, all the arguments for it were terrible. So I already lost the fight. I don't know why I keep relitigating this, but we got plus and minus grades, and we don't have to use them. So what if I just decide that passing gives you an A? Oh, what are we talking about? Oh, yes, functions of parameterized curves need to be backwards compatible with functions. I don't know how I started thinking about grades. I think it's because I have a lot of grading to do, and I don't really want to do it. All right. So we need a few examples. First, we need our iconic example of a parameterized curve. That's going to be the unit circle. Because it just goes back to trig and say, hey, remember trig? Yep, that was a parameterized curve. We just didn't tell you it was a parameterized curve at the time. And then we need to make this backwards compatible with other things. So let's do the example everyone uses. There's a reason that everyone uses an example. We're familiar with it. And it's a good place to start. That makes it a good place to start. Go ahead and start your campaign in a tavern. It's familiar. Everybody knows what's going on. Perfectly acceptable. So we know that if we want to describe when we have a unit circle, when we have a unit circle, we decide what the coordinates of a point are. The coordinates of any point, theta units up from x, is going to be cosine of t, cosine theta, sine theta. And this goes all the way around for theta equals 0 all the way up to 2 pi. So this point here is where theta equals 0 and where theta equals 2 pi. So we can describe the unit circle, instead of using the equation x squared plus y squared equals 1, we can describe it with these parameters. So I could say x of t, I switch from theta to t. Oh well. X of t is cosine of t, y of t is sine t. And then we should specify what values of t we want people to plug in. Plug in all the t from 0 to 2 pi. There's a parameterization of the unit circle. Any questions? So parameterized functions or parameterized curves is a thing that we've been doing since trigonometry. We just might not have used the words parameterized curve. Any questions? Comments? Notice that this description of the unit circle is compatible with our equation for the unit circle. So this description is compatible with the equation of a circle. In rectangular coordinates, the equation of a circle is x squared plus y squared is equal to 1. If I replace x with cosine of t and y with sine of t, this equation says cosine squared t plus sine squared t is equal to 1. And that is true. That's our Pythagorean identity. Cosine squared plus sine squared is equal to 1. So it's compatible with our previous description of the unit circle, x squared plus y squared equals 1. Any questions? So we need to spend a few days looking at more examples of parameterized curves. We also needed an example where this parameterization of curves is backwards compatible with stuff that we have already. So I needed to combine those into one example since I was running out of space and time. So the whole continuum was collapsing on me, partially because I was babbling on about grades. The only conclusion we were able to draw at that point was that if we're going to agree to this competitive model for schooling, then the only grade that matters is A. If we actually cared about about learning stuff and educating people, then we should all literally be satisfied by getting a C in all of our classes. Because that is by definition what a C represents. C is satisfactory by definition. So if you get all C's in your classes, you should be satisfied with that performance by definition. But you're in a STEM field and you have to go through a good program as if that means something. And then, so you can get your job as a, I don't know, I'm not allowed to look. Any questions? Comments? Snide remarks? All right, so tomorrow and Friday, we'll look at some more examples of parameterized curves. That's going to do it for today. Everybody have a good day. I'll see you tomorrow, and thanks for playing.